Hello explorers and welcome to another video. Today we are going to tackle day 6 of the advent of code, and we are up bright and early, exactly when it releases, so just a few seconds has gone, so let's just jump right into it. So here, the seafloor is getting steeper. Maybe the sleigh keys got carried this way. A massive school of flowing lanterfish swims past. They must spawn quickly to reach such a large numbers, maybe exponentially quickly. You should model their growth rate for sure. Although you know nothing about the specific species of lanterfish, you make some guesses about their attributes. Surely, each lanterfish creates new lanterfish once every 7 days. However, this process isn't necessarily synchronized between every lanterfish. One lanterfish might have 2 days until it creates another lanterfish, while other might have 4. So you can model each fish as a single number that represents the number of days until it's created a new lanterfish. Furthermore, you reason a new lanterfish should surely need slightly longer before it's capable of producing more lanterfish, 2 more days for its cycle. So suppose you have a lanterfish with the interval timer value of 3. After 1 day, its interval timer becomes 2. After another day, the interval timer becomes 1. And after another day, the interval timer becomes 0. After another day, the interval timer resets to 6, and it should create new lanterfish with the interval of 8. After another day, the first lanterfish have an interval timer of 5, and the second lanterfish have an interval timer of 7. A lanterfish that creates new fish resets its timer to 6, not 7, because 0 is included as a valid timer value. The new lanterfish starts with an interval timer of 8 and does not start counting down until the next day. Realizing that what you are trying to do, the submarine automatically produces a list of ages of several hundred nearby lanterfish, your puzzle input. For example, suppose you were given the following list. 3, 4, 3, 2. This list means that first fish has the interval timer of 3, the second fish has an interval timer of 4, and so on until the fifth fish, which has the interval timer of 2. Simulating this fish over several days would produce as follows. Initial state, and then they go to this, so it resets to 6, and this up here will be 8. And then after 3 days, these two will produce a new lanterfish. Okay. So here that one produces a new lanterfish, so it goes over here and then it becomes 6. These two produce new lanterfish and becomes 6. And then this becomes 6. So when these have arrived down here, they start over at 6 and so on. Each day a 0 becomes a 6 and adds 8 to the end of the list. Well, other number decreases by 1 if it was present at the start of the day. In this example, after 18 days, there are a total of 26 fish. After 80 days, there would be a total of 5,934. Find a way to simulate lanterfish. How many lanterfish would there be after 80 days? And then we have our puzzle input. So we need to save that first off. So let's do this. Day 6. So let's do some simulation. So first off, we need to have our initial fish here. And let's see how day 5 is modeled here, or day 6 is modeled. So it's just one line with a bunch of numbers. Okay, so we actually don't really need to have this reader that we usually use. We could just say that we have string test, and that would be those numbers, and then we will have the data would be the actual input. It will be a long line, but it will be fine. So now we can skip that part and just consider string s of test split on that. And now we need a fish class. Of course we need a fish class. So let's see here, new class fish. So days to reproduce, and that would be 8 to start with. And then we would have public static void final. Let's see here, public void inc day, and then we will just take day to reproduce minus minus. Fish has child. So let's see if this fish has a child this day. So if days to reproduce is equal to 0, then days to reproduce is equal to 6, and we will return a new fish. And public void init int days, so we need to be able to set days to reproduce. So we need to have a start value there. And if not, we will return null. So now we can have a fish that will be increased every day, and then we will check if every fish has a new child after we have done other things. So here we will have a list of fish. Sea. So all the fishes in the sea. New array list. And we will fix that list as well. So let's start here by creating a new fish. And then we'll take this fish and we will init it with integer parse int s. So we will have a bunch of fishes there, and we will set an initial values for them. Then we will need to do something for 80 days. 80. So first we will have a for loop of every fish in sea, in the sea, under the sea. Let's see here. Has child, fish, child. If child is not equal to null, then we will add it to the sea. Fish. There we go. And then we will have another one which will increment the days here. Increment days. And that could be just like that. And down here we will have C size and print that out. Let's see what that says. What that gives us for the first. Oh, we started day 5, which is the wrong day. So let's run day 6 instead. We got 0. Okay. So that's interesting. How could we get 0 fishes in the sea? That's not really reasonable, right? So let's see here. We have the test input. We will, oh, that's very reasonable, I would say. If we don't add any fishes to the sea, then we don't have any fishes in the sea. So let's just add some fishes to the sea. 6 for co-modification. Okay. So we can't add to a list while. So we will have a new list of fish, children, new array list. So here we'll add to the children list, and then we will have them added down here. So C add all children. So let's go for that. Then we got 15,820, and that's not the right number. So if we go 1 earlier, just to see that we didn't, no. So we did something else that was not correct. So let's see here. If we go here, we debug this, then we should have 5 fishes in the sea. That's correct. And we can give the fishes a toString. Like that. And we just have days. We skip the rest of this fish thing. So let's see here, if we do that and restart this, what do we get? They should be more readable. Yeah, so now we have 3 days, 4 days, 3 days, 1 day, 2 day. Okay, next iteration, they have gone down 1, so that's correct. Oh, we iterate that before we, so we need to add the children after we have incremented that day. Let's see what happens then. Well, it got less. So let's see. So there we have a 0. Oh, the fishes need to be reset to 7 so we can increment that day as well. Could that be it? So now it becomes 6, yeah. Yes. And then we get 2 new fishes. So this seems reasonable. Yeah, so now we have 5, 9, 3, 4. So first off, we needed to add the children afterwards, and the fish incrementation, as we do that after we have checked if we have new children, we have the problem that the counter will be increased for the ones that have exactly now reproduced. So we need to set that one higher. So let's see what we get if we do the full data set now. Go over to data, run that instead. Then we get 352,195. So let's put that in and see what we get. You get a gold star, I get a gold star, everybody gets a gold star. Nice. Let's go over to part 2. Let's see. Part 2. Suppose the lanterfish live forever and have unlimited food and space. Would they take over the entire ocean? After 256 days in the example above, there would be a total of 2, 6, 9, 8, 4, 4, 5, 7, 5, 3, 9 lanterfish. How many lanterfish would there be after 256 days? Okay. So if we just change this to 256 and change over to our test data, we will get what? It will take a little while. So this is probably a space problem. Could we fit it into the space allotted to us? And it takes a little while to run. And we hear the computer ramping up. Hopefully we don't crash. So now we are talking math here. This is probably something that you could simplify by using more math. And if I can, I will simplify it by using more CPU and memory. Yeah, so we ran out of Java heap space. That was expected. And so we will get more and more and more memory usage here. And we will use quite a lot of it. So we need to figure out a smart way of using a lot of memory. So having that many fishes would not work. But if we do it as a string, we conserve a lot of space. Right? So let's go back to the earlier examples of 80 days here and remove our array list. We will stop reading things, and we don't have any children. So we go through the list of our test data. String work data equal to test. So let's go through each work data, and we will split that on that instead. And here we'll do int children equal to 0. And we'll also have string new work data, and that's an empty string, like that. And we will also have a boolean first equal to false. Oh, true. If first, if not first, then new work data is equal to no. We can fix that with the children later on. So let's see. We go here, and we will string children. We have a counter for that already. So integer parse int of f int fish. So we just have the number of the fish here. If the fish is equal to 0, then it needs to reproduce. So we will take children and add that, and fish will become 7. Okay, now the fish becomes 6. Else fish, we decrement fish, and new work data is equal to fish plus a new comma. So that's what we do then. And here we will take work data will become new work data, for int I of the So let's see here. each next round there will become a child. So we decrement every yeah, so here we go up to 6 again, yeah. So now we just need to figure out how to add the new children. So perhaps it's even better to just have like that. First, false, true. If not first, we will add to children. Extra comma. And we set first to false down here. So now I'm doing this, everything with just adding. Oh, for instance, we could do yeah, we need one less. So the first one we don't need that on, and then we can just have children here. And then when we are done, we will just check the work data. Divided by 2. So perhaps we can just do like that and then skip the last line. That could be also if f is blank, continue. So let's see here if we check this out. How is this working? So we have work data, which is that. Yeah, so we should go up here. Okay, work data became something totally different. Work data plus children down here. Let's try that again. So we go through here and we will pick up the first fish and decrement that and add it again. So now we will have a new work data. And then we'll do the same again, new work data. Oh, we need to add to the new work data. Of course. Why didn't I do that? Always good when you debug. Let's try it again. So we get new work data. We add to it, we get new values, and then we go up here to the next. So we get that work data, which was this one, right? Yeah. So if we run this through, we should get the same result. We got the same result. And we hopefully used a lot less memory in the process. If we change up to 256 days, could we do this? There's a lot of loops, a lot of work going into it. But it might be doable. At least we're not using same amount of memory here as before. Using a lot less memory. Even though strings are not the most conservative memory structures we have, they are less than full classes at least. But it can take a while to run this. So let's see. I'm wondering here, now that I'm sitting and thinking about this, doesn't every fish contribute to the final result equally? So if we have one fish and it reproduces and creates offspring, that offspring will create new offsprings in the same tempo, independent of the other fish. So perhaps we can make this simpler by changing this up and doing each fish by themselves. So for instance, if we do work data, because that will also mean a lot less memory to use in each iteration. So work data, test, split on that. So that will be our work data. And then we just put the full algorithm in here, like that. And then we will take this work data and increment to fishes, like that, add it to fishes, and then we will print that out. If we do that, we should get the same result over 80 days, yes. And hopefully that will be faster because we will only look at one fish at a time. So hopefully this will work better with less memory and faster, even over 256 days. Perhaps we even could reuse our fish model that we had before. It still will take a while to run, of course, and there will be a lot of parsing, a lot of loops and so on. But we will use less memory. So we have around 300 fishes here instead of 5. So if this takes an hour to run, then we don't have 300 hours to run the other things. But if it's a couple of minutes, we can do it. Let's see here. 300 divided by 5 is 60. So anything that we come up to is multiplied by 60. So if it's 3 minutes, it's 3 hours. Another thing we can do is using more cores. So that will use a little bit more memory, but will take a little bit less time. So then each fish would be one core. And count their fishes and get the result back. So let's create a new fish core, because that's hardcore, and it will implement callable int gear, implement method call, so that will give you an integer back, and the fish public fish core will have a string of work data. This work data is equal to work data, create field, or start data. Like that. And then we will just take everything in here. Into our fish core, and that's what we want to return. And then we'll take string work data equals to start data. So then each core can work on one fish, pretty much, and return our value. In that case, we would have for loop of what we have here, and then we will have fish core, work. Let's see here. We would have something called executor. Executor service, we would have executor service, and that would be let's see, executor service. Want one of those, new fixed thread pool, executors. Let's say that we have 5 threads in our pool. Submit callable task. New work fish core, work data, yes. So we want to get the result back from our callable. So we submit a task, we will get the future back. Okay. List future result, new array list. Add that future. With callable example. So we want to have all the results back. So we get some futures, but we want all the results back. And we have a get here for each of these. So we await the termination and we get the result list, and then we have a shutdown there. Yeah. We wait for hours instead. And we will have this function as well. Result. Get result list. Yeah, we can call it result list. That's fine by me. So we get the number, and we will add that to fishes. That. And go back here. So let's go back to 80. Stop this one and see if we can run this in 5 cores and get the right result. Okay, so let's change that to 5 seconds as they suggested. 1, 2, 3, 4, 5. And there we got the result. And we also need to have ES shutdown. So we actually shut down the service. 1, 2, 3, 4, 5. And there it shut down. So we can go back here and have 256 instead. And try that. And hopefully this will be in endless time. And we are back, and it has been a while. I started this early this morning, and now it's really late this evening. It's not the next day yet, but it's pretty close. So it's a quarter to midnight. So, and we have actually a result here. You see, I have a really large number here. And it's 6 million. Let's see. So it's million. So yeah, really large number. Let's see if it is the correct number. So let's switch over here, put it in, and submit. Yeah, you get a gold star. I get a gold star. Everybody gets a gold star. So we actually found the right value. And the reason why it took so long is because the tests with the thing that I survived to build took 5 hours to run, and then I had to run the real data, which also took 5 hours to run, because I figured out how to do this in a really nice way so it will take not as much time. And you see here that I have results for different values, and this is because there are 5 different kinds of fishes depending on which day they start. Either they start on day 5, 4, 3, 2, or 1, and then I just figure out how many of those fishes there are and multiply my results with that. And you see each run here took 4 hours, 4 hours, 4 hours, and the last one took 5 hours and 19 minutes. And of course, I ran these in parallels, so I used 5 processors or 5 threads over 5 hours in order to get this result. So let's go through a little bit what I've been through here. So first off, I thought, okay, this would never fly with just having a bunch of classes, so let's try to do this with strings instead. That was extremely slow. Did not fly at all. Next up, I tried to implement something that took an output stream and then read a lot of bytes and so on, and I ran out of memory. And I tried with a byte buffer, ran out of memory. So the last solution was actually to use files on disk. So with this, I've also used 25 gigabytes of data, because I realized that the 256 here, that's a byte. So if I remove, for instance, 1 or so, I will end up in the range of a byte. Then I just can use bytes and save them to disk. And first off, we have an executor service here. So I've started up something here. I ran it with 6 threads in case I got more than that. And then I put a bunch of jobs up here, and I take this days counter that we have up here, so the number here 4, 1, and so on. So I pick that days counter, and I see if I have any jobs that is on that specific day, and if not, I will create a new fish core, which is a job with the number of total days minus the days that have already elapsed with this specific fish, or how many needs to elapse until the fish will reproduce. So I will decrement that value there and create a job ID data directory where it will put files. And then I will increment the job ID, and if I find multiple of this, I will increment this counter that I will multiply with for each of these jobs. So for instance, up here, if we got 1, then we will create 1. Then here we will increment, and so on. And then I will invoke all those jobs, wait 5 seconds after everything is invoked, and then just start waiting for the results here. And when everything is done, I will add my fishes up and print out the last result. So if we look here, this is the last result we printed out, and I also have printed the duration here. So these 5 up here is the actual fish core that's reporting back. So let's look at the fish core. we can start at the beginning here where I have some private variables. I have a temporary directory. It's a working folder where it will save different files. And I have a start value, and this is the value that the number of days it starts on. So it's the number of total days minus the days the fish needs to wait until it can reproduce. And I will create my temp folder here, and I will start the output file as 0. So the first file that I will write to is 0. And then I will just print that specific number into this specific file. So I start up with a file with 1 byte in it. And then I have this little call function here where I start off with a big integer where I will save my value with it, which is fishes. I will start the little instance here so I can see how long it takes. And then I will create a byte array, days to live. And I will have that at 32 kilobytes in order to read data from disk pretty fast. And then I have this file ID that I can increment. So the first thing I do is open the file in my temp directory here with file ID 0, which is the first one. And I will have a read variable that is 0, so that's how many bytes I have read. And then I will increment my file ID and create an output file, because this is where I want to write my data when I'm done. If I read anything, then I can continue, but if I haven't read anything, I want to break down here and don't go any further. I should have had these close before these, yeah. But it doesn't really matter if I close the last file. But if I haven't read anything, then I don't have any more fishes to handle, so then I will break. So this while loop here, so I will break out of this while true here. So this while loop here will read the file and read these byte buffers over and over. So I read a byte buffer, and I will set that I have read anything if the byte array is not -1, which is I couldn't find any data. So I found some data here, and then I will go through j until the number read, so I can increment through the full buffer. And then I will take the first value of the buffer and I will increment over that value. So if we say that this is days that this fish will reproduce, and then I will take the first time and I will decrement 7, because 7 is the amount of days that it takes for the fish to reproduce again. It says 6, but it's actually 6 until 0, which is 7. So it's actually 7 days until the next time it can reproduce. And if the value is less than or more than -9, which is the time it takes for the new fish, the new child, until it can reproduce. So if the time is less than 9 days, or more than 9 days, I will type that value out. If it's less, then this fish will never reproduce again, so I will put that to 0. So I know that I don't get any minus value and get anything strange there. So this fish will not reproduce anymore. It's a 0. So next time it will not be handled in this function up here. Because you see here that I had to take this byte, which is a signed value, and remove the sign. And if I hadn't put this to 0 here and got the minus value, then this would be a really large value, and I don't want that. Very important. And after I have run through this for loop here, I will add 1 fish, because now I have handled 1 fish. And then I will read the next one and the next one and the next one until I've read all the fishes of this file. And that will actually create perhaps a doubly large file. So it will be a very much larger file. And then I will flush the values out after each of these read procedures. and then I will close that file, and then I will start over. So as I incremented the file ID here, the next time I come up here, I will read file number 1, and I will write to file number 2, and so on and so on. So I will get directories with files in them. I'm not sure if this is showing here, but here we have a directory, and we have a bunch of files in this directory with different sizes. I think this was a directory with something large. So here I actually ended up with 2 files of 1 gigabyte in size. So that's what I used in order to get this result. And I tried a lot of different things until I actually found something that worked. And I guess if you are good at math and paid attention in school, you could do this just on the back of a napkin with pen and paper. But as I don't really figure out all these permutations and so on, I wanted to do it the more brute force way of actually creating a model and running it through and calculating how much the fishes will reproduce. I hope that you found this interesting. I hope that you learned something today. If you have a more elegant solution, you probably have, leave that in the comment section down below. If you like this video, give it a like, share it with your friends and colleagues. If you haven't subscribed yet, please do that. And I really hope to see you in the next video.